There we go. All right, note to self. Let's get that set up. All right. Sorry about the late start. Attendance is going around. Make sure you sign that. And then you have homework due today. So you can turn that in at the end of class or online before midnight if you want. Doesn't matter to me. And I think, did I make your project due today or Thursday? Today? Okay, so make sure that you turn that in also now or online as well. Okay. Oh, one more thing. Are you able to view your Canvas grades now? Yes, good. Okay. Didn't realize that was an issue before, but it should be correct now. Louder. Grades up to homeworks 3 and 4. The rest are nope.
We only got 1 and 2. At least from what I see.
Okay, I'll double check that. Canvas is a little slow to update sometimes, but question.
So I have a question about the project.
Yes.
For number 9, there's an S.
That's not supposed to be an S.
Thank God.
Yeah.
What is it supposed to be?
I thought I changed that. Is it not fixed in the new document? Okay, yeah, I updated it. You might have the old version.
I was writing on a PDF, so.
Okay. Yeah. Okay. All right. Any quick questions about that stuff before we get started? Yeah. Yeah, they were only due on Thursdays because I was uploading them late. That's fine. Anything else? I saw a hand over here. Okay. Well, let's go ahead and get started then. Today we're talking about more compartmental analysis, basically mixing problems, but we're talking about population models, so the framing's a little bit different. We have 4 sections today, quick outline. Let's just do a quick review of what compartmental analysis is. So it's that general framework. We drew graphs and wait till we're ready. Okay. So compartmental analysis is that general framework where we drew graphs and then we assigned a quantity to each node in the graph, and the arrows gave us the flows in and out of those nodes. So we originally used that for mixing problems, and we used this rate principle. So the rate of change of a quantity in a compartment is the difference between the flow in and the flow out. How much stuff you got coming in, how much stuff you got going out. So this is our general model for anything that has to do with compartmental analysis. You can modify it slightly, but we're not doing that in this class. And we had graphs that looked sort of like this, where, okay, here's our node in the middle. This is the one we care about here. There could be various sources contributing to the inflow, and then various places contributing to the outflow. All right, and we just say, all right, how much is coming in? 3 minus how much is coming out? 2. So we can do the same sort of stuff with populations. We've got some cute little otters down here, give us a sort of a visual approximation of what's going on. So populations often are grouped into demographics, you know, different ages, if you're looking at TV ratings, or, you know, maybe you're trying to figure out how a university's enrollment changes over time. You could group people into, again, ages, whether they are transfer students or freshmen coming in from high school. You can look at other demographics, whether they're international students or domestic, or whether you're out of state. So all sorts of different things can be done with populations. And usually what we want to do is model the size of a particular population over time. So say, all right, students between the ages of 25 and 30 over the years from 1970 to 2010. And similarly to the mixing problems, we have inputs and outputs. Population is P, it's got an initial size that changes over time. And the inputs usually come from what are generally called births. So you can think of this as, maybe the population of a country. And immigration, these are external agents that come in to include a population. If you're thinking about P as this an age demographic, then immigration could be, I don't know if you can have immigration. These two might be the same, and you're thinking of just people becoming 25 years old or becoming 31 years old. Right? So they're no longer in this population, or they are newly in the population. Right? And you've got little otters making little otters, and then other otters dying off. And you have these populations that change over time. Right, so there's only one. We don't like otters dying. They're very cute. All right, so what do the models look like? Well, we have to make assumptions, right? So for all of our models, we make assumptions to give ourselves things we can actually work with. We make assumptions for population models about the flows. We did the same things with the mixing problems, but we didn't really frame it that way. So for population models, you want to worry a little bit more about how things are coming into or leaving the population. So the first one is, all right, we need sort of a general principle here. More members means that there are more opportunities to reproduce, means that there are more opportunities to die. Right? If you have a lot of things and you check each one of those things, there's a chance that one thing, maybe a piece of bacteria, can create another bacterium, or maybe an otter, unfortunately, may die off. Right? But there's a chance associated with each of those. So we get these, I phrased that weirdly, flows due to birth and death might be proportional to the current population size, right? Using this reason. So we get this formula for the inflow, which is some proportionality constant times the current population. And then outflow, same thing, different proportionality constant times the current population. So you can go ahead and pop these into our rate principle, which is dp dt equals the difference in the flows. And since we have the same p in both, we can factor it out and just write this as a single parameter. So this is called a one parameter model. It's only got one little extra variable there that you find out from experiment or data. And then your initial value. Okay, so this is our basic, very simple population model. It's called the Malthusian model or the exponential model. Oh, by the way, I posted these slides maybe 5 minutes before class if you want to follow along on there. I just realized that it may be annoying for me to slide quickly. So what about the solution of the Malthusian model? The solution is an exponential function. We've seen these sorts of equations. This is separable. You bring the p over to the other side and integrate both sides, and you get this solution out after solving for the constant of integration. But because we have this parameter k in here now, we get different looking solutions depending on the sign of that growth parameter. So originally, I often said that k was going to be positive all the time, right? We did that with like Newton's law of cooling, I think, and maybe Newton's laws of motion. We mentioned the air resistance should always be a positive number, or the coefficient should be positive. But here we want to worry about this parameter, which is the proportionality constant for growth and decay combined into one, which means, okay, maybe decay is larger than growth. Populations are dying off faster than they're growing. I think that's an issue in places like Japan right now. And so we get different looking solutions based on the values of K there. Right? If K is positive, in this model, you get exponential growth versus negative gives you decay, or K could be 0 and you get constant. This is rare. So we have an example here. In 1800, US population is about 5.3 million, and in 1900, 76.2 million. Go ahead and use the exponential model to predict the size of the population 100 years later. I'll give you a couple minutes for that. See if you get some number out, and then we'll see if this graph actually works.
We got mapped it out now.
Well, is it 17? I'm asking you to use the model to predict the size. Is it 17? Probably not.
So for T, just like change of times, like instead of P of 1800 or P of 900, like P0, P like 100 or something like that.
Sure, you could set 0 to 1.
Yeah, so it's gonna be more lesser equal P10 P.
I saw something about like the next thing you get like
All of them will do that.
So we're saying, so instead of times 0. I think we need to find K. So we use my research. There you go. Or well, what I'm saying is plug in this one. To find like yeah, there's different age. Yeah, so they have to make I was gonna use one. Wait, I have a quick question. So, that's the 5.3. That's the initial.
Sorry?
The would that be 5.3?
It depends on how you choose to write that, but yeah.
Because that would be the initial. So it's 76.2. Oh, then that's a bonus fund. Because I didn't find it 3.3. Yeah, that's. Well, I got 1, 2,
Okay. 420. Let's go ahead and do this so we don't waste too much time. Anybody get a number? 87.6. Sounds plausible. Okay, it might be. Let's go ahead and try and solve this real quick. Did I give myself space? No. Okay. So we have our solution here. P equals C e to the kt. Right. C was our constant of integration. K was that one parameter in our model. And we have two pieces of information. Now, we get to sort of set the scales for these. These are pretty large numbers, so I probably don't want to write down 5.3 times 10 to the 6th every time I need to write down an initial condition. So what I'm going to do is instead, I'll take this number, set it to be my 0, t equals 0, and I'll take this number and just not write million. Right? It'll be 5.3 is the value. And so that'll mean that my p is being measured in millions, and my time is being measured starting at 1800. And then the other thing that I'll do is, again, 1900 is pretty far from 1800. So I will set the scale to be 100 years is 1. So time will be measured in hundreds of years. So what we have here is p of 0 equals 5.3. And then all of that scaling stuff I just said means that we have p of 1 is 76.2. And we want the value of p of 2, or question mark, because that is 100 years plus 100 more years past 1800, which would be exactly 2000. Okay, well, I have a solution to my model here and two pieces of data and two unknown parameters. I can use those to find C and K. Find C and K. And then once I have those, I can compute P of 2. Okay. So let's see how much space we can do that. So we've got P of 0 equals 5.3, and that means that 5.3 should equal C times e to the k times 0. And 76.2 should equal c times e to the k times 1. Okay, well, e to the 0 is 1, so we just get the value of c outright as 5.3. And then here, if we solve for k, we should get the natural log of 76.2 divided by 5.3. Now, I am 100% certain that at least a few of you tried to compute this number using your calculators. If you got that point, you probably want to get a decimal out. You don't have to do that at all. Watch what happens next. P of 2 is 5.3 e to the natural log 76.2 over 5.3 times 2. One of my log rules says that that 2 get popped up here as a square. And then I don't have any coefficients in front of that log, so I can cancel it with the exponential. And this gives me 5.3 times 76.2 over 5.3 squared. And if you want, you can cancel one of those 5.3s. And we'll get 76.2 squared over 5.3. Now, isn't that going to be a little bit easier to plug into your calculator? Let's see what that is. Actually, I have my actual calculator over here. You got a number already? $76.2, square it, and divide by 5.3. Okay, I'm getting a little bit bigger than 87. I am getting 1,095, or let's just round it to 1,096. That's pretty darn big. It's saying 1,096 million in 2000. Well, that doesn't sound right, does it? I don't think we have a billion people in the US just yet. So the exponential model kind of works, but it doesn't predict that far out. I'm going to see if this graph or link to a graph actually works. Okay, no, unfortunately, I cannot show you that graph. If I have time at the end of class, I'll see if I can pull that up for you. It's a regression showing the actual data for the US population. And I just wanted to show you how it kind of almost matches the exponential model, but sort of towards the end does not match exponentials very well. So let's just move on then. Okay, so the exponential model has problems. It's unbounded over time, but the solutions are unbounded. Meaning, all right, as time goes on, the population just gets bigger and bigger and bigger and bigger and bigger with no cap. And that is cap. So the model needs to change a little bit if we want to reflect reality. Okay, so whenever we change our model, we need some new assumptions. If our model gave us something that didn't reflect reality, it means we assumed something wrong that was maybe close for what we thought originally, but it doesn't actually work. It's not really how things work in the real world. So here are our new assumptions. Input, we'll keep this the same. We don't want to complicate too much. Output, we can change. So this is saying that the way people die off, or the way that people leave a population, or agents leave a population in general, might be a little bit more complicated than just someone dies. It might be that it's a little bit more like, well, when two people interact, there's a chance that one of them dies, right? This is sort of modeling like a crime interaction. So if two people get in a fight, someone shoots the other one, and then you have a death, right? So the number of deaths is proportional to the number of two-party interactions here. And this is why this is p squared. Two-party interactions, if you have like 3 agents in the population, well, you can have someone interact with themselves. This person can interact with the first person. The third person can interact with the first person and the second person. Second person can interact with the first and the third. And these interactions all have a chance of one agent being killed, right? And then a decrease in the population. You could also change the input to two-party interactions to more accurately represent births, right? That would also depend on the population that you're looking at, though. So if we're modeling people, it might be more realistic to make this p squared. But if we're modeling something that reproduces asexually, then it might be better to keep that as just p, right? So bacteria, or I think snails maybe, can reproduce asexually. Then you get just a regular p to the 1 term. Okay. All right. So now we have a 2-parameter model, because I can't just factor out the p now and have 2 constants added together. Now I have p and p squared. So if I try to factor out a p, I get standard way to write this, p times k1 minus k2 times p. Okay, so we have this new model here. So another example. Investigate the behavior of solutions to the following differential equation. Okay. So I'll give you a minute or two to just answer these 2 questions for yourselves. See what you can figure out, and then we'll talk about it.
I got home at 4. We went to bed at 2:30.
And Charles will take something old from mine. So if I don't leave before 7 a.m., I don't make it to school until after. Either to get to school an hour early, or that's all I haven't gotten my. We're gonna say 17.3.
No, no, really. No. Considering my grade is so weak, probably didn't get that too.
Yeah, so it's the function. But we have slightly different models. I'm just going to be a little bit more complex. And that's what we want to analyze here. All right, so let's, with some good questions, let's go ahead and analyze this model. So we're given a differential equation, and every time we see one of those, it's a good idea to try and classify it into one of the types that we've already solved. What kind of differential equation is this one? It's a couple of different kinds, but what kind of differential equation is this? Separable. What else could it be? Not quite. That piece squared makes it not linear. What else though? Something almost linear. No. That's definitely, did I hear Bernoulli? Yes. Yeah, take that credit. Yeah, it's a Bernoulli equation. Okay, so you can treat this as separable or Bernoulli and get a solution out of it. Separable and Bernoulli. Okay, so what can we say about the model using only the equation? Usually we find a solution and then start talking about the behavior of that function. But for some differential equations, it's really hard to solve them, and it's a good idea to learn how to understand the values of p without finding that solution. And this is a very, very good model for learning that. So are there any obvious constant solutions is usually a good question to ask. And what happens when the initial condition changes? This is actually very important later on. If you end up taking, I think it's called 3171, you'll talk more about this stuff. But you remember when we were talking about the Picard-Lindelof theorem, and we said existence and uniqueness were two important things for differential equations? This is the third one. So we have existence, uniqueness, and then this, which is called continuous dependence. I can't spell. On initial conditions. Right. So usually for our differential equations, we want the solutions to change nicely as the initial conditions change. We don't want like a big change in how our solution looks if we go from 80 to 81. That would be kind of annoying. Okay, so let's answer these questions. So we have a first order DE. We'll work through some observations. It's a first order differential equation. Usually means we can solve for the derivative. And in this case, we can. It's in the form of some function of the population. Oh, it's in the form of some function of the population. The derivative doesn't show up, or the derivative doesn't have a t in it. T doesn't show up on the right side of this equation. These have a name, they're called autonomous DEs. Okay. What else? Well, what about constant solutions? That was our one of our questions. If the derivative is equal to 0, that corresponds to a constant, right? Then this part implies that the solution has to be constant, right? Because the derivative being 0 at some point t, well, there's no dependence on t for the derivative. So if it's 0 anywhere, it's 0 everywhere. Okay. So if the derivative is equal to 0 at some point, then we know the solution is constant. Okay. The behavior of p between the constant solutions is determined by the sign of f of p. And actually, let me go back for a second and let's just find those constant solutions. We have 0.5p minus 0.004 p squared. That factors p times 0.5 minus 0.004 p. And if this is equal to 0, then we have either p equals 0 or p equals 0.5 divided by 0.004, or 500 divided by 4 is 125. So those are the two roots of this function, and they are also places where the derivative is 0 and where the population is constant. So if the population starts there, it never changes. This part makes sense. This part is a steady state, an equilibrium solution. Okay, so we said the behavior of the solution p between those values, if we start with an initial condition of 80, gives us, or is determined by the sign of this function in between there. So you remember when you were doing, what are those called? Solving inequalities or optimizing functions, finding rates of, or intervals of increasing and decreasing in calculus 1. You drew these tables where you say, okay, I've got like x minus 3, 2x plus 1, and then I'd put 3 or minus 1/2, 3, and then infinity minus infinity here. And say, all right, x is, or this is negative here, positive there, negative here, positive there, and then so my function is positive, negative, positive, that sort of thing. Same thing happens here, only now we have p instead of t that we're doing this with. Okay. Last part is that that function f that we had is a polynomial, so it's continuous in p. And what that does is it guarantees us that dp dt doesn't change sign anywhere except at those roots. So the population won't go from 80 and increasing to 81 and decreasing because it doesn't cross a root there. Right. You have to cross 125 or 0 in order to change sign. All right. So let's draw something called a phase diagram. So phase line looks like this. And I want 2 dots in here. So 1 dot for each equilibrium solution. And we'll label those. So this is 0, 125, and these are minus infinity and infinity. Notice also that this is a line or an axis for p and not t. It's horizontal, which is annoying, but it's easier to draw them in small spaces like this if they're horizontal. Okay, and then so what do we do in between? Well, we figure out whether the function is, the function f is positive or negative. So is f greater than 0 or less than 0 in each of these regions. You can go ahead and check, but it'll turn out that this function is positive here, negative here, and negative, or should be positive here, I believe. I don't remember exactly what that one is. But that's okay. These ones are more important anyway. What happens is that the population, if it's between 0 and 125, should be increasing. And the population, if it's between 125 and infinity, it should be decreasing. Basically, this is saying, if you're up here, you've got too many people in your population, and there's not enough resources. Eventually, they're going to start dying out, and you'll get closer to your equilibrium solution here. But if you're down here, you're in the sweet spot. This means that you don't have too many people, and there are enough resources to go around, so your population can grow. You've given your bacteria in the petri dish a lot of food. Okay. So, if f is greater than 0, then derivative is also greater than 0. If it's less than 0, then the derivative is also less than 0. So each one of those cases is reflected there. And you can check this part if you want, but this corresponds to a negative population, and that's not really physical. So we don't have to worry too much about less than 0. It should be negative, I think. Oh, by the way, these are called trajectories. They don't look like what you normally call a trajectory, but if you were to expand this along t, you would see an actual curve. So we'll go ahead and actually solve this equation now. So we've got the derivative is what's that? K1p minus K2p squared. And we can treat this as separable or Bernoulli. I like Bernoulli right now, so we'll do that. If we rewrite this, we've got the derivative minus K1p equals K2 or minus K2p squared. Divide by p squared. And multiply by -1. And we'll get, let's say W equals p to the -1. So that'll be our substitution for Bernoulli, and we'll end up with this equation. Plus K1W equals K2. All right. Your integrating factor in this case will be e to the K1t. So that's our mu. And our solution here will be e to the K1t times W equals, what is that, K2 over K1? E to the K1t plus C. Okay. And then remember W is 1 over P. So we've got this for our solution here. I'm realizing I'm doing this in general by accident. That's fine. E to the K1t. We want to solve this for P. So we have P equals e to the K1t over K2 over K1 e to the K1t plus C. Okay, and then our initial condition was P of 0 equals 80. At this point, maybe we can plug in some numbers, since I did that more in general than I meant to. K1 equals 0.5, K2 equals 0.004. K2 over K1 is 1 over 125. And so we've got 80 equals 1 over 125 plus C. We can solve that for C. We should get 1 over 80 minus 1 over 125. Okay. And then I don't care to find out what that is. Actually, calculator here, we can do that. 1 over 80 minus 1 over 125. Getting 0.0045 for that. Okay. So there's our solution. 0.5t over 1 over 125 plus 0.0045. Okay. So in general, we have this model, which is what I just solved by accident.
You go back for a second.
Sure, yeah. Anyone else need more time? Okay. In general, you want to analyze the behavioral of solutions to the following DE. So you have the same differential equation, I just haven't put numbers in for the parameters or the initial conditions. And that gives us, well, what I solved a second ago. P of t equals e to the k1t over k2 over k1 e to the k1t plus, and then over here we actually have 1 over p0 minus 1 over what I'm going to call p infinity. And p infinity is k1 divided by k2. It is the second steady state solution of our system, aside from 0. Okay. You might notice that also over here, this is 1 over p infinity. So we can rewrite our differential equation as this. Okay. Make our differential equation look like that instead. We rewrite things a little bit. All right, so that's our solution. And we can analyze it. What are our constant or steady state solutions? Oh, we've got P0, no, not P0. P equals 0 or P equal P infinity K1 over K2. That's what's written down here. That is the limiting value. If you have a population that's between 0 and that limiting value, it will try to increase according to this model towards the limiting value. If you have a population that starts above this number, then the population will start to decrease towards that number. Right? So this is where everybody wants to go. It's our happy medium. It's called the carrying capacity. It's what your resources and your situation can afford to allow. So we can do what I just did a second ago. Your differential equation can be rewritten like this. One minus 1 over p over p infinity. So your model can be rewritten that way. And then the solution, like we just saw, can be rewritten as p of t equals, actually I'm going to write it slightly differently. What was that? P infinity over p0 minus 1 e to the minus k1t and then plus p and or 1, I think. Okay. Just shifting stuff around a little bit. So again, remember I mentioned that continuous dependence on initial conditions is important. That solution doesn't depend continuously on the initial condition. Over here, you have 1 over P0 right here. So if P0 is equal to 0, you get discontinuities. All right. There's another thing that we have to worry about, and that's when this whole denominator is equal to 0. But what happens when P0 is actually equal to 0? Well, in the original model, our initial condition is 0. That means that we have no population to begin with at all. So this is the constant solution 0. Right? It means you didn't have anyone to measure growth or decay of. If P0 is not equal to 0, but the denominator of P is equal to 0, we can solve for T. So let's do that. We get P, what was that? I'm here. P infinity over P0 minus 1 e to the minus K1T plus 1 equals 0. Okay, and we can solve that for T. And this should give us T star equals something like minus 1 over K log 1 plus P infinity over P0. That's what I have written in my notes, but I might have made a mistake over here. It should be something like this. Okay. So you can solve for T is the important part. And you get a number that is not infinity, right? If P infinity is a number, P0 is not 0, K is something determined from experiment. This gives us an actual number. There's not a minus there, actually. But this is a point where we got division by 0 in our solution for P here. So what's happening? Well, this is when the population blows up. It's called a finite time blow up. At that time, the population is infinite. So the logistic model also has some weirdness happening. All right, so go ahead and try this practice example. I'll give you until 5 o'clock, and then we'll move on to the rest of our stuff. So remember, you don't actually have to solve that differential equation anymore. You can use the solution that you wrote down.
So this one, T0 starting at P0 would be 4.3, right? So we're at what? 260. But you're right. But yeah. Oh,
Right after you make that. I didn't know that. So, right.
Yeah.
It's like not divisible by.
Like,
What? What? You can't make a square or a rectangle.
How often are they? That's what you do. Like 17. I don't know how to use Excel.
Right, but so I realize you do that. You say prime, you go top right.
I have 3 of them.
Oh. In the midterm, I didn't do it.
Yeah, you're already in the stack.
Yeah, I didn't know.
It's like you said, like, you're all bunch of arrows on everything.
Yeah, exactly. I made a 50. Oh, you did. If you think about it. I understood this shit on the next.
All right, it's 5 o'clock. Let's try and get through this. If we go quickly enough, I might be able to let you out a little early. Actually, I think in the interest of time, I'm not going to try to solve this one so I can show you the other models. But I'll describe it real quick. It's more or less the same thing that we did for the previous example that I had you practice. You use this data to plug into the solution that you already have, and then use that to solve for your now 3 parameters: constant of integration, and then K1 and K2, or K1 and P infinity, whichever of those you like.
So would 1800 be like P of 0 3?
Yes, you could do that. I can write that down at least. Yeah, so you would set something like P of T is whatever it was. P of 0 is, let's say, 5.3. P of 1 now, that's setting a scale. P is measured in hundreds of years again. 76.2. And now P of 2 is 281.4. So now you just use those 3 pieces of information like we did for the last problem. So notice we're not doing a whole lot of actual solving of differential equations in these examples. You're just using what you already have to do some calculation and prediction. And that's more or less what we want to do with differential equations. We want to get solutions and then never have to solve for them again. I guess this is some good information. The logistic model and the more complicated models are actually kind of difficult to deal with by hand. Usually these would be plugged into a computer and you just put in like some data, or you give it the parameters and it gives you a graph. Okay, so what about other models? Again, it's not perfect. The logistic model has some weirdnesses to it. What can we do to improve our model? You can modify it in a couple of different ways, but again, always using new assumptions. So what we've already been using is called the density dependent hypothesis. And it says the rate at which the population grows only depends on the current population and not on time, right? If the rate at which the population grows depends on time, it means you have extra factors that are influencing things. Things like birth rate laws are an example of that. Right? If you're allowed to only have so many children at a certain period of years, then, well, the birth rate's going to change because of that. at a different time versus in that time. So this is what our model looks like when we have the density dependent hypothesis working. And that gave us these, the inflow and outflow rates. Different choices of the function f give us different models. If you choose f to be a constant, you get the exponential model. If you choose x to be a linear function like this, you get the logistic model. What else can you choose f to be? So well, you can do this, which doesn't account for f. You can add in an extra term, like immigration or emigration. So if this is positive, you have immigration. If it's negative, you have emigration. This is like net. It's the net for immigration plus emigration. I don't know what the word is for that. Net migration. Or maybe just migration is what it's called. That's better. Migration. And you have creation and destruction. This is more of a physics terminology. Those are more complex. You might have things like, depending on different types of interactions, you can change the exponents right there. So we changed the exponent to 2 to get two-party interactions. If you change it to 3, you're dealing with three-party interactions. If you change it to 1.5, a little harder to interpret, but one person plus maybe some weird interpretation of half a person. Right? Probably a better interpretation of this is using creation and destruction. This might be something like the number of a type of particle in a particle accelerator. So if you go to like the Large Hadron Collider in Europe, they care about the number of particles that they measure over time. So you might have to look at a whole bunch of different types of particles colliding in order to get one specific particle, which increases your population, right? Or maybe lots of different particles interact to give you a net 0 particles, and then everything is gone. Okay, so one fancy modification changes the rate of growth there. So it takes a specific value of f, it sets it to almost linear, except you have log of p right there. So basically your assumption is that the deaths do not happen polynomially, so not necessarily just based on the interaction, but a little bit less than that. So death based on interaction is pretty rare, actually. I mean, I'm interacting with you all right here, and none of you are dying. If you consider all possible interactions, oh yeah, right? Differential equations is pretty crazy. If you consider all possible interactions over the entire country, it's going to be pretty small fraction of those interactions where someone ends up dying. Okay. So what this does is it allows your solutions to grow a little bit more quickly, right? While still being below some number. Okay. Which hopefully is more realistic. So solving the differential equation, here's an example. And again, in the interest of time, I'm just going to do this one. So we want to analyze the behavior of the given DE and solve it subject to the given initial condition. So, sorry. No, stop. Vicky, you're making it hard to teach my class. Okay, we were talking about analyzing the differential equation. So again, you can factor this thing out. P times 0.5 minus 0.04 log P. And now you have your 0 solution. And then you also have log P equals 125. This means that your steady state solution is now e to the 125 power. That's a lot bigger. So I just said that this differential equation allows your solutions to get bigger, which hopefully is more realistic. It gives you more space to grow. So let's go ahead and solve this. It has a different looking solution. What did I want to treat this one as? I think I'm going to treat this one as separable this time, because it's not Bernoulli. doesn't have a power of p there, and it's not linear. So it's easier to solve this one if I write it like this. 1 over p a minus b log p. P equals integral dt. This left side, you can take this part to be u. And then du is going to end up being minus b over p. So we have an integral that looks like, let's do this, minus 1 over b integral minus b over p, 1 over a minus b log p. Okay. This and this give us du, and this right here is 1 over u. So we have minus 1 over b integral 1 over u du equals, and then on the other side we have t plus c. We can go ahead and multiply things through. We get log absolute value of u equals minus b times t plus c, and then u equals c e to the minus b t, and finally substitute back in for u, and we'll get something kind of neat. So this is a minus b log p. If you solve that for p, you have to take another exponential. So what we get here is, let's see, b log p equals a minus c, let's just say plus c e to the minus bt, divide by b, and then p equals e to the a over b plus c e to the minus bt. So you have a double exponential here. So the Gompertz models behave very, very weirdly, but the graphs actually look pretty similar to the logistic graphs. The growth just happens according to a weird function as well. Okay, so there's our solution. And models like the Gompertz and logistic equations can be applied to a lot more than just actual populations. So you can think about the number of cells in a tumor, and people actually do this. If you look at some medical papers, you'll see, or on tumors specifically, you'll see things called metabolic curves. And these talk about the rate at which your tumors are growing, right? So you want to measure those metabolic curves, and hopefully they are getting smaller, not bigger, right? That means that you're losing, your cancer is shrinking, not growing. The spread of disease happens a lot. People actually did this a whole lot when COVID-19 was first popping up. There are tons of videos on YouTube of people trying to analyze like the value of R, which is a standard parameter in one of the disease models. Cool one is that you can measure the number of articles of the English Wikipedia using a population model. As people add or change articles, they merge them, all sorts of stuff like that can be modeled using a population model. And then the last one that is, I think is kind of neat, is chemical reactions. So if you take, what do they call that, PChem, sometimes you'll actually have to solve differential equations. And during reaction kinetics, you might see differential equations like that. This one is a little bit different because now it's a quadratic polynomial with one non-zero root, or two non-zero roots. Here's just an example of a model or a problem where you might have to deal with that. I'm not going to solve it in 2 minutes, but that's more or less what you would be given for a chemical reaction example. Okay, that's all I've got for you. Make sure that you give me your homework before you leave. If you're turning in your project here, do that too. Yeah. Put one on top.
You said we could turn it tonight.
Yeah, if you want to turn it online, that's fine. Uh-huh. Okay, you can start.
Oh, you're gonna love this.
Yeah.
The beer question for problem 9. You want to know what I got?
What'd you get?
194 degrees. You not want your beer at double, triple the room temperature? You not enjoy beer at 194?
I didn't write that
I
problem.
said question mark and I tried, but then I was thinking, I divided it by 3 and that's like 67. And
Okay.
That's less than room temperature, so just take the divided by 3.
Okay, all right.
Thanks.
I'll double check that problem. I don't have the solution to
I
that.
had an exam before class and I came in late.
Okay. As long as you're here.
I took my
Why are you
project.
using about this?
That's fine.
It's a thing.
Yeah,
Yeah, so we can turn that stuff in before midnight.
yeah.
Online.
Online is fine.
Okay, I'll send you the email. I'll just
Okay,
disregard that.
no worries.
Thank you so much.
I didn't put my project together,
That's fine.
but I did write my name on every single one of them just in case.
Okay,
And this time I put this up here, so we'll find it easier.
okay. Well, this time I'll have time to alphabetize them, so that'll be helpful.
After being in class in 15 minutes.
How do you say your last name? Picararo?
Yeah, pretty much.
Picararo? Pretty much.
It's Italian.